Chapter 2, Chemistry Comes to Life. Matter is the term to anything that takes up space and has mass. Different forms of matter include solid, liquids, gas. Matter is made up of atoms. Each atom contains a nucleus with protons and neutrons. These are surrounded by a cloud of electrons. Atoms are units of matter that cannot be broken down into simpler substances by ordinary chemical means. Electrons with the most energy are furthest from the nucleus, and the chemical properties of an atom are determined by the number of electrons located in its outer shell. If you notice under A, you have an atom of helium with your protons and your neutrons. Protons having a positive charge, neutrons a neutral or no charge located within the nucleus. And in the outer shell, it shows 2 electrons with a negative charge. If you look to the under C, you show an atom of oxygen. It has 8 protons and 8 neutrons located within the nucleus. You notice 2 electrons in the first shell surrounding the nucleus. That is the maximum number that shell can hold. Then you see 6 located in the second shell. The second shell can hold a maximum of 8 atoms. Thus, a molecule of water, H2O, would be 2 atoms of hydrogen, 1 atom of oxygen, because hydrogen has 1 electron. So thus, when a molecule, atom of oxygen binds with 2 molecules of hydrogen, that satisfies the requirement of an octet rule, or 8 electrons in that outer shell. So thus, that shell's happy and it will not bind any more. So H2O would contain the 6 electrons from the oxygen plus the 2 electrons from each of the hydrogen atoms. An element is a form of matter that cannot be broken down into simpler substances, and this is made of atoms that are all the same, such as oxygen is an atom. Each element has an atomic number and atomic weight. The atomic number is the number of protons in the nucleus, whereas the atomic weight is the number of protons plus the number of neutrons. Such as oxygen is an atom, O2 would be considered a molecule, where H2O would be considered a compound. There's only about 20 elements found in the human body: carbon, hydrogen, oxygen, nitrogen, sodium, calcium, so on. Oxygen would be the major element in the human body. This shows the periodic table located in your textbook that you can review. You see hydrogen that we talked about earlier. It's got 1 electron, so thus when it binds with oxygen, if you look over to the far right, you see oxygen. It has the 8 protons, 8 neutrons. It had 8 electrons, so thus the 2 were in the first shell with the 6 remaining in the second shell. Thus when it binds the 2 hydrogen, it becomes H2O. Elements with the same number of protons but different numbers of neutrons are called isotopes. All carbon atoms have 6 protons in the nucleus. Common isotopes of carbon include C12 with 6 neutrons, C13 with 7 neutrons, and C14 with 8 neutrons. there's more than 300 isotopes that occur naturally. Radiation is energy moving through space, such as radio waves, heat, and light. Some elements have both stable and unstable isotopes. A radioisotope is unstable and emits radiation. Radiation can be harmful, causing the death of cells, or can be beneficial, as evidenced by its use in medicine, wherein radioactive seeds may be planted in the prostate to treat prostate cancer. Radioactive iodine, which helps to visualize internal organs, and radiation, which is used to cure some cancer. Approximately 60 isotopes occur naturally, while others are designed in laboratories. Damage from harmful radiation can affect low white blood cell count, development of cancers, and damage to organs and glands. The most common burn from radiation is perhaps from the ultraviolet radiation of the sun, and therefore it's important to use effective sunscreen when outside in the sun. This is an image shown in your textbook of where radioactive iodine images are used to detect abnormalities in the thyroid gland, so it has a useful purpose. Two or more elements may combine to form a compound, and the characteristics of a compound are usually different from those of its element. A compound would be like sodium chloride, which would be like the addition of sodium plus chloride, or a molecule of compound of water such as H2O, which would be an atom of oxygen plus 2 atoms of hydrogen to form a compound. The atoms in a compound are held together by either covalent or ionic bonds. When atoms form bonds, they lose, gain, or share electrons in their outermost shell. Covalent bonds are the strongest. Covalent bonds form when 2 or more atoms share the electrons in their outer shells. Ionic bonds, on the other hand, involve the transfer of electrons from one atom to another. A molecule is a chemical structure held together by covalent bonds, and the chemical structure shows the number of each element forming the molecule, such as 2 or more atoms. Molecule would be like sucrose, which would have be represented by like C12H22O11, which just means it's got 12 carbon atoms, 22 hydrogen, and 11 oxygen. An ion is an atom or group of atoms with either a positive or a negative electrical charge. Ionic bonds are weaker than covalent bonds. Ionic bonds result from the attraction of oppositely charged ions rather than shared electrons, such as the sodium chloride, sodium having a positive charge, chloride having a negative charge. That would be an example of resulting from the oppositely charged ions. This shows the sodium, which is a positive charge, plus the chloride. So an atom of sodium transfers the electron from its outer shell to the atom of chlorine. Having given up the electron, sodium becomes a positively charged ion. Chloride, having received an electron, becomes a negatively charged ion. And so sodium chloride, the oppositely charged sodium and chloride ions are attracted to one another, forming sodium chloride. The positive notation just simply means that it has one more proton than electron. In the negative, it has one more electron than a proton, giving it a negative charge. When the electrons of a covalent bond are shared unequally, the bond is called polar. The resulting molecules are called polar molecules, and water is an example of a polar molecule. Water, with its unique properties such as its high heat capacity, its high heat of vaporization, and its superior ability as a dissolving agent, can be traced to this polarity. Covalent bonding electrons may be shared unequally or equally. Electrons shared in water, H2O, spend more time near oxygen than hydrogen, thus making oxygen slightly negative and hydrogen slightly positive. Hydrogen bonds is the interaction between two polar molecules. Hydrogen bonds is the interaction between two polar molecules. The attraction formed between a slightly positive charged hydrogen atom and another slightly charged. Hydrogen bonds is the interaction between two polar molecules. Hydrogen bond is the attraction formed between a slightly positive charged hydrogen atom and another slightly negatively charged atom. Hydrogen bonds accounts for the unique properties of water and the geometric shapes of many biological molecules such as proteins and DNA. Acids and bases react differently to water. Acids release hydrogen ions when placed in water, whereas bases produce hydroxide ions when added to water. So acids release hydrogen ions, whereas bases produce hydroxide ions. pH is the term given to the negative logarithm of the concentration of hydrogen ions in solution. So pH measures the quantity of hydrogen ions. The lower the pH on the pH scale, the greater the acidity. The higher the pH, the more basic a solution. So this shows the pH scale where acidity would be from, say, 10.0 to 10.7. Neutral being considered 10.7. You notice human blood runs around 7.45. Basic or alkaline runs from roughly 10.7 to 10.14. Baking soda would be a basic or alkaline. Acidic would be on the lower end of the scale. And so it's very important to maintain appropriate pH in the body, because even just a slight change in pH in the blood can result from death. Each unit is a 10 times increase. So 5 is 10 times more acidic than 6 on the pH scale. 5 would be 100 times more acidic than 7. 5 would be 1,000 times more acidic than 8. So the pH in the stomach, once that food arrives, is roughly around a 2. Blood is around 7.45. Buffers are substances consisting of either weak acids or bases, and these buffers are designed to maintain a specific pH of a solution. Buffers prevent dramatic changes in pH. Buffers remove excess hydrogen ions from solutions when concentrations of hydrogen ions increase. Buffer systems add hydrogen ions when concentrations of hydrogen ions decrease. Many body fluids have the buffering capacity to maintain this constant internal environment. pH drop from 7.4 in the blood to 7.0, or an increase to even 7.8 can result in death in just a few minutes. We have a carbonic acid and bicarbonate system in our blood that helps to keep the pH around 7.4. And almost all biochemical reactions of the body occur around 7.0, with the exception of the stomach in digestion. The pH around 2.0 is maintained by stomach cells producing hydrochloric acid, which helps